Very good morning to all. And again, I welcome you all to this short 1 hour webinar. It will be conducted on one of the important topics is a new manufacturing process, so 3D printing or the additive manufacturing. This is really gaining its importance today as a manufacturing process or sometime at its coming days, it may replace some of the manufacturing processes. In this context, is one of the important developing process it is. We have organized a webinar to understand more about it. And I would like to introduce today's speaker also, one Mr. Vaman Kulkarni. He is a pioneer to develop AM technology in the country very effectively for last 10 years. Industry recognizes him as an AM expert and has been the chairperson for several AM conferences and workshops. He is a review panel of MH1 mentor with AMTDC IIT Chennai. He worked for 14 years with the Honeywell Technology Solution as director and worked for 21 years with the DRDO as a group director.
Thanks, Ramesh and Ganapati from IMTMA for enabling this webinar. Also, thanks for that nice introduction about myself and Mr. Venkatraman, together whom we started this 2V3D organization. I'll be talking about the different additive manufacturing processes, the applications, and then the benefits. That should give a very good input to all the participants. Why additive manufacturing is being talked as the future technology of manufacturing. In the country, there has been a very big focus on additive manufacturing, especially in the last 5 years. The reason is India has typically not done well in the area of manufacturing. We still have a lot of dependency from the external manufacturing agencies. Being a new technology, we have a big opportunity to play a bigger role and then be self-sufficient as part of Atmanirbhar Bharat. Ministry of Heavy Industries as well as the Ministry of IT have been promoting this technology in the country in a very, very big way. There has been a lot of investment which has been happening both in building the infrastructure as well as the skill development, which is very much essential if we have to play a much bigger role. Not just in the country, I think we have enough opportunity to play a bigger role even in the global entity, as this is a technology, and if we have the right technology as well as the right people who can drive it, then I think we should be able to play a much bigger role. With that introduction, many of you may know what is additive manufacturing, but for the people who don't know, it is a process where we build the part layer by layer and by using the 3D CAD model. So that's the process is about. Conventionally, what you see here in the top row here is a subtractive way of manufacturing, or what we call it as a conventional manufacturing, wherein we take a bar stock and then we remove the material to the shape and size what we want, and then in the process we have a lot of wastage which is happening, and then we also need a tool here to remove the material. So that's the process which we are all used to. But in the additive manufacturing, the part is built layer by layer, and the input what is used is the 3D CAD model. That 3D CAD model will decide the shape of each layer, and then also the layer thickness of each layer what is to be built. Because of that, we don't need any tooling as part of this additive manufacturing process. We may have to do a small post processing or a finishing operations on the build part to maybe achieve the finish or some of the dimensional accuracy which we cannot directly achieve, or in some cases we don't need any post processing at all. So, and in the process we have very little wastage. So conventionally this process is also are called as 3D printing or the rapid prototyping. In fact, it's not a technology which has come up recently. It has been there for last 35, 40 years. But in the last 30, 35 years, the technology was limited to the simple plastic materials with which we can make the components. And it was mainly used for prototyping activities, either for visualization purposes or for carrying out some assembly checks, or to also take it to the customer and then give so that he can have the visual visualization of the product. So for that, it was limited to that purpose. But in the last 10 years, this technology has grown a lot. And now we can build the parts with metals, different types of metals, almost any metals, standard materials like stainless steel, the aluminum alloys or the titanium alloys or the nickel alloys, cobalt, chrome, so gold, silver. So there's a variety of materials what the additive manufacturing can handle with the current technology. And of course, the variety of plastic materials, right from the ABS plastic to the polyamides, the nylons, the rubbers, you name many of the polymers, I think it can be done today. And it has also been extended to the ceramics and then the composites today, and including the construction material. So that's the reason why this technology has become very popular. And then we say that this is going to be the future technology which industry will be adopting to address many of the manufacturing challenges or how to reduce the manufacturing time. Typically, I tell all the people that it is not that additive manufacturing will replace the conventional manufacturing. It only complements the conventional manufacturing or the subtractive manufacturing. It works together. The subtractive as well as the conventional manufacturing will work together to bring speed into the manufacturing activities and also address the challenges which may be there when you have certain designs which cannot be done with the subtractive way of manufacturing. This is a good example to show that typically how the additive manufacturing process has some benefits over the conventional manufacturing. A typical teacup, if this teacup has to be manufactured with the conventional machining, maybe like a CNC, so we need to create this, you need to take a bar stock, then create this internal cavity, and then we have to do the machining to get this undercut. And then you have to, this handle need to be a separate part, and then you may use either the welding or the brazing or the soldering to fix this. And then you have to machine the bottom. So there are multiple processes which are involved to finish this component. Whereas the same cup, if it has to be done through the additive manufacturing, it will be done just as a one single assembly, and then it starts from the bottom, like building the base, and then as the layers builds up, it gets the shape and size what we want. So that's a good example to see that how additive manufacturing simplifies the manufacturing process. So as I told, 3D CAD file is an important input for this additive manufacturing process. And then using this 3D CAD file, the parts are built layer by layer, and then we get to the shape and size what we want. The typical AM process consists of these 5 steps. So first, most important thing is the creation of solid model. Most of the current day youngsters, they prepare their drawings as well as the 3D models with the CAD softwares. Maybe it is SolidWorks or the CATIA or AutoCAD. So, but typically most of them are familiar with that. But there is an additional technology which is involved when you prepare the 3D model for the additive manufacturing. So that is the knowledge which the engineers need to add on to the CAD knowledge what they have, so that they can make the model which is additive manufacturing friendly. And once we have that model, typically it is converted into a neutral file format, what we call it as the STL file. The reason is the STL file is a neutral format which can be opened in many of the CAD softwares, as well as the pre-processing software which most of the machine manufacturers provide. So also we need to ensure that when the model is converted to the STL file, we should not face any problem, and with some of the features may not be completely captured. So that's the additional care we need to ensure that the STL file is properly captures all the features. Then we do the pre-processing on that model. The pre-processing depends on the AM process what we are following, and then also it depends on the machine manufacturer. If it is for the plastic part, then there are some plastic machine manufacturers. They have their own softwares, or there are some standard softwares like Magix, Cura, and other things, which is being used by many of the machine manufacturers. But ultimately, the pre-processing we do it so that one is to decide on the layer size, and then slice the model to depending on that layer size. And also, if we have to provide any of the supports, we need to generate some of the supports. And it also decides the orientation in which the part can be built. See, since its part is built layer by layer, we can always print it a different orientation. So what is the best way to build the part so that it will have minimum support and it will take lesser time? And also, you will not have to do much of the post-processing once a part is built. So that's again a technology which is involved in the pre-processing. And once that is done, typically a G code or a AM code which is generated, which is downloaded to the machine, and then machine reads that code, and then it starts building the part layer by layer. Once the part is built, then we have to do some post-processing operations on that. A simple cleaning operations is one which is typically done always. In addition to that, we may also have to do some stress relieving. There could be some residual stresses which could be there when you build the part, and you may have to do that stress relieving operations. Or you may have to, if you have to do some certain heat treatment and other processes, we can still do it. And then if we want to do further machining or to get the dimensional accuracy or the surface finish what you want, you may do some of the additional machining to get to the final part what you want. So typically this is the process, and each of these process steps is a technology. Just to tell you, in Honeywell about 10 years back, when we built our own state-of-the-art additive manufacturing lab, there were hardly a couple of them in the country who were doing it, and we have to learn it in a hard way. And our success rate of building the part was only like about 1 in 4. If we build the 4 parts, we used to successfully make only 1 part. The other parts either will have some cracks, or it may get interrupted while printing. So once we master this technology of the model as well as the pre-processing and then setting up the right machine parameters, then I think we've been successful, and within a couple of years, I think we understood all that. And then, of course, today the technology has much improved. There is a lot of automation which has happened to enable this. But as a AM person in the organization, you need to understand all this technology. So what are all the AM processes and then the materials which are available today to the industry? This is the way the additive manufacturing process has been classified by the ASTM. There are basically 7 types of additive manufacturing processes. And whatever process, the new ones which comes up, ASTM is able to classify among these 7 types of the processes. The first one is the photopolymerization, VAT photopolymerization. It was also called as the stereolithography. In fact, this is a technology which was there almost 35-40 years back. And it was limited to the plastic here. And you can also see the dots what I have put in here. These dot indicates what is the raw material type. VAT polymerization uses liquid. liquid as the raw material, and then either you use the thermal source or the any other light source, basically photo source or the thermal source, to solidify that liquid. And then, of course, both the solidification as well as the layer thickness are controlled so that you finally build the part. Subsequent to stereolithography, there are other things which are also come in, like the liquid thermal polymerization or the beam interbase solidification. They are all classified under the stereolithography process. The next process which came into existence around 1990 is the material extrusion. In fact, one of the important things as part of this is the fused deposition modeling, FDM technology, which came into existence. The Stratasys was a company who initially came up, and then they put a patent around that complete technology. And they were the only people who were allowed to use this technology for almost 20 years till this patent expired. And then there is a lot of people who have entered into this market. So the technology here is, the material is in the form of a filament or a wire, and then that wire moves through a nozzle, and the nozzle is heated. So as the wire moves extruded through the nozzle, the wire melts, and then the nozzle moves in the X and Y direction to get to to build the part to the shape and size what we want. And then, of course, once one layer is done, and then that solidifies, and the next layer is built on top of that. And because of the simplicity, and then the accuracy which you can part, and then the type of polymers and the plastics what it can handle, it's become very popular. And today a lot of applications are there using the FDM technology. And also there are a lot of players today. In fact, the machine cost has come down drastically from 2015 onwards, depending on the accuracy of part what you want to build. The third process is the direct energy deposition. So this is here the raw material is in the form of a powder, and then we typically use the laser source or the electron beam source to melt that powder. So it's typically a process wherein you start adding the material on top of an existing part. In fact, this has been there. In fact, for last 25-30 years, this was used as the technology where we can repair the part or salvage the part. Some parts may get rejected, especially the complex part, very late, and we realize that during the assembly stage, and then we can salvage that by using this direct energy deposition, where we can build on top of the existing part and get to the shape where it fits into the assembly. This is very widely used in many of the aerospace and space applications, as well as in the automobile industry, especially when you have a complex part. Of course, the accuracy to which you can build the part depends on how well you can control the layer thickness as well as the laser. The powder bed fusion is a technology which is very, very widely used for all the metals today. And this is the technology which has come up in the last 10 years. Here, the raw material is in the form of a powder. That's where the technology is called as a powder bed fusion. And then the fusion or the sintering is done through a power source, which could be a laser or the electron beam. You have a layer of powder spread on the bed, and then you move the layer in the direction to get to the shape and size what you want. And it is done in an inert atmosphere of either the nitrogen or the argon gas, and the heating and cooling cycle happens for each layer. And once the first layer is sintered and then it solidifies, then on top of that you spread the second powder layer, and then the process repeats. So as I mentioned, the process involves the heating and cooling. There could be some residual thermal stresses which needs to be relieved post the part is built. the technology which is either direct metal laser sintering or the electron beam melting and then the selective laser melting. These technologies are all very, very popular today. There are a lot of machine manufacturers who produce these machines which can handle various types of metals. As I mentioned earlier, it could be the nickel alloys or the stainless steel, different types of stainless steel, aluminum alloys, the titanium alloys, cobalt, chrome, most of the materials which is used in the industries. And in fact, this process is not just limited to metals. It can also be used for the high temperature polymers and then the plastics like PTFE or the PEEK, and those are the other things which can be used with this technology. The next one is the binder jetting technology. The binder jetting technology is similar to the powder bed, but it uses the binding material. The binding material holds the particles together, and because of the binding material, initially this technology was not very widely used because the property of the part what we build is not comparable with the original alloy. But in the last 4 or 5 years, the technology has improved where the binding material melts off, and then only the alloy material is held together. And because of that, the properties are very close to the original alloy. And the other advantage of binder jetting is the size limitation, which could be there in the powder bed fusion, is not there in the binder jetting. So we can build the much larger parts. So this technology is a growing technology, and then it's getting applied into the different industries. The material jetting technology is similar to the inkjet printing, wherein the raw material could be either in the form of a liquid or in the form of a powder, and that powder flows through the nozzle, and then it solidifies, and then you build the part. Typically limited to the plastic and then the polymers, low temperature plastics and polymers. The advantage is you can use the multi materials with the material jetting technology. The sheet lamination is where the raw material is in the form of a sheets, and the thin sheets, and then the sheets are laminated one over the other, and then we heat that sheet so that it binds together and then holds on. In fact, this technology has been there earlier, but now it is also classified under the additive manufacturing technologies. Basically, for the sheet metal parts, this technology is used. So that's the wide range of processes what we deploy for the additive manufacturing. The materials which are there for additive, so that material plays a big role in producing the quality of parts using this additive manufacturing, whether it is FDM process or it is the laser sintering process or the material jetting. The powder plays, the raw material plays a big role. That will decide the strength of the part, whether it is tensile, compressive strength, or the fatigue strength is all decided by the alloy as well as the purity of the alloy, and then its geometric parameters that plays a big role. And it also decides the surface finish of the part, and then the accuracy of part what we can build. So the raw material is another important part of the AM industry, and it is a special process, especially when you have to have a powder. They use a process what is called as the automation process, wherein we control the size of the size and shape of the part, and then you also control the distribution of the particle sizes, and then the oxygen and nitrogen content, and then the density of the powder. So these are the important properties which needs to be controlled. And there is a lot of material science and metallurgy involved. In fact, there is a lot of research and development happens around this whenever a new material is developed for additive manufacturing process. The microstructural analysis, as well as once the part is built, then if there are any blowholes or the cracks, how that can be controlled by properly controlling the energy source, plays a big role in building the good quality additive manufacturing part. So this table, I will not go through in detail this table, but just to give you a glimpse of the The material types, as I told, it could be polymers, the metals, ceramics, or even the composites. Then what AM processes is used? If it is a polymer, as I mentioned, the most common process which is used is either the laser sintering or the fusion deposition modeling or the 3D printing. So these are the technologies which is very widely used for a wide range of plastic materials, whether it could be a thermoplastic or it is thermosetting type of things. And you can see the range of materials what is used. So almost all the polymer variants which are used in the across the industries is all possible to be done out of additive manufacturing today. And for the metals, the technology is basically the laser or the electron beam technology, which is used. It's called the either could be called as the laser sintering or the laser melting, what we call it. And then you can see the range of materials which it is covered today. And this is growing every day. In fact, earlier in the somewhere about 4 to 5 months back, copper was not easily printable. And the Objectify company in Delhi, so they came out and optimized the laser process so that they can build the copper alloy also using the additive manufacturing. And as you know, copper is a very good component, especially for the many of the heat exchanger applications. And similarly, the ceramics. So ceramics could be done either through the FDM process or through the sintering process, or through the electron beam melting process. And then we can variety of ceramics, whether it is aluminum based or the zirconium based. So all that silica based, all those composite ceramics can be done out of additive manufacturing. Similarly, the composites, you can see that whether it is a polymer to metal composite or the polymer ceramic composites or the metal composites or the carbon reinforced plastics, all that could be done out of additive manufacturing. And even the functionally graded materials, where the property of the material varies across the dimension of the component. So with such varying strength components can also be produced through additive manufacturing, either by having the different materials or introducing some of the blowholes or the gaps in the way you build the property, or it can be done through the cellular structures. So that's the process and then the materials. I'll talk the applications and benefits together so that you will understand in a better way. One of the big application where we get the benefit of additive manufacturing is in the weight reduction. Because the way the part is built, it is easy to build a part with taking out the material where it is not needed, depending on the functioning of the part. As a good example here, what is shown is the seat buckle, which is used in the aircraft, and of course, it's also used in the many of the automobile applications also. And typically, this is made of conventional steel, and the part is designed this way so that it is easy to produce, and then it keeping the cost also into consideration using the conventional manufacturing. This buckle typically weighs about 150 grams. And now with additive manufacturing, if you just modify this design, and you need to ensure that you are meeting all the functionality of the part, but wherever there is an opportunity to take out that material, you can do that so that the weight reduces from 150 grams to around 70 grams now. And since you are manufacturing out of additive manufacturing, this part is very, very easy to manufacture with additive manufacturing. We never conceived this type of design because manufacturing this out of using the conventional machining is very time consuming, as well as it costs a lot. So that's the benefit what you see when you design it fresh, keeping the additive manufacturing in mind. And in an aircraft, every gram of weight what you save, it leads to the fuel efficiency. In fact, there are in an Airbus 380 aircraft, where there are about 800 seats, you save a weight of 72.5 kg. And just imagine over the life of the aircraft, what is the fuel saving as well as the economy of which benefits what you get out of this. So this is a good example, especially on the weight reduction. There is a lot of applications. The topology optimization is one of the design tool wherein you can optimize the geometry, keeping the how the stress distribution happens in the component. For example, this bracket, you can see that there are a lot of areas where there are very low stresses and you can take out that material. So by optimizing, you can reduce the weight almost by more than 50%. In fact, this is one of the engine mounts which Honeywell we designed, wherein you can optimize it by reducing the weight. And this is the low pressure turbine blade, which is used in, which is done by General Electric for their Lipex engine aircraft, where the weight is reduced by more than 50%, and the cycle time reduction is also 75%. So this is one of the big benefits what we get from additive manufacturing, wherein we can optimize the weight without affecting any of the functionality. And in additive manufacturing, one of the cost element is decided by the powder or the raw material what you are using. By optimizing the weight, you're also reducing the powder consumption, and you're also reducing the time what it takes to build that part. And then, of course, ultimately, all that helps in reducing the cost. The other big application is the customization. Wherever a customization is required, that can be easily done by additive manufacturing. There are few reasons why it can be done very easily, because there are no tools involved in the additive manufacturing. And customization doesn't involve multiple processes which are involved. It is just one single process where you are building the part. And any feedback you get from the customers for the customization can easily be done. Whereas with the conventional manufacturing, it is very difficult. Whether you do the turning, milling operations, or you use the casting or the forging applications, there are tools which are involved. And any changes to that design, you also have to modify the tools and then the manufacturing process. The example what I'm showing here is for the medical application, and this is just an example, but as I mentioned, wherever customization is required, that can easily be done. In the dental applications, the crowns which are used, in fact, every individual is different, and you cannot have any standardization here. And of course, it also needs very high strength, and most of this thing is done out of titanium, and which is printable material with additive manufacturing. So it is easy to get the imprint and then create the CAD model, and then print the crowns using this. So the dental industry is using this in a very, very big way, leveraging the additive manufacturing for these applications. Similarly, the implants could be for many of the surgeries related, especially the orthopedic and other surgeries where you need those implants. Whether it is for the final surgery, or it is sometimes when you want, the doctors do a complex surgery, they simulate the surgery process, and these implants are used during that simulation exercise, so that they finalize the surgery process before they actually do the surgery. So there's a big application of customization which is required in the biomedical industry, and additive manufacturing has been very widely used. Then the complexity of the part to which you can build using the additive manufacturing. You need to make the part more complex so that you get a better performance. That is one thing. Other one is you can make the component at a lesser weight, and then you can make it out at a lower cost. With additive manufacturing, irrespective of the complexity of the part, the cost doesn't vary much. It's almost flat. Whereas with the conventional manufacturing, if the part is very simple, then the cost could be less. But as the complexity increases, the cost increases exponentially. That is where you start getting the benefits of additive manufacturing for the complex designs. In fact, there are a lot of applications of additive manufacturing where you can come out with a very innovative products, leveraging additive manufacturing, so that some of the limitations what we had of manufacturing such components with conventional manufacturing is addressed very easily. and you can get the best performance from the designs. So the innovative design is I'm just showing one of the example where the cellular structure, the designs, cellular structures or the helicoil designs, structure designs was known 20, 30 years back, but the applications were very limited because of the difficulty in manufacturing this. But now with additive manufacturing, all this is possible. So you can have improve the strength to weight ratio or the heat transfer rate or the thermal insulations, or also you can have a part which has a negative Poisson's ratio and then good for acoustic purposes. So all that design is very, very easily possible leveraging the additive manufacturing application. In fact, this is one of the straight tube duct. Of course, as all of you know, that heat transfer depends purely on the surface area, and you can improve the surface area by having this type of cellular structures, and then you can almost get more than double the heat exchanger efficiencies, additive manufacturing. So the tube duct can add the multifunction here. Apart from transferring the flow, for transferring the fluid, it also can do the heat transfer function. Then the fourth big advantage is on the part consolidation. So you can consolidate the parts together as one single assembly. Typically, for example, this fuel nozzle, which is a standard example, which is talked about by every additive manufacturing professional. This is a part which is made by General Electric for their LEAP-X engine, which is there in the Boeing 737 MAX aircraft. So this is typically made out of 20 parts, but this is now converted into one single assembly. So in the process, you have eliminated the assembly fixtures which are required, and then you eliminated the special processes like brazing and laser welding and other things which were required, and then reduce the uncertainties which are involved during the assembly process. So that way, and also manage the number of parts. So that's the big advantage of consolidating the parts. Now, so that's why when you do the additive manufacturing, you just check the adjacent parts and then see whether all the parts can be consolidated into one single assembly. Heat exchanger is another part. This is also a part which is there in the flying aircraft. This is Boeing 737 MAX. This has typically about 163 parts, but with additive manufacturing, it's just one single part with weight reduction of 40% and then the cost reduction of 25%. So those are the part consolidation benefit what you get from additive manufacturing. Some more examples, you can see this is a bicycle which is typically would have made at least some 15 components, but now the entire thing, the frame, the wheel, as well as the handle, and then the seat, everything is made out of one single assembly. So those are the big benefits what you get from additive manufacturing. Apart from the material savings, what we talk about, there is no tools in which involved, and the reduced inventory. I typically talk about this staircase type of model, how the industry is adopting this technology for different applications. Typically, as I mentioned, even when the metal was not there, only the low temperature plastic was there, it was still used for all these prototype and then tooling type of activities. And that is continue to be used even with metal coming in for all the prototyping type of applications, where it reduces the product development cycle time. In fact, I'll show with some of examples. The product development cycle time could be reduced as high as 70%. And since it is not getting into the final production, we are not really bothered about the volumes and the cost which is involved, especially the high volume ones. The additive manufacturing may not be cost efficient, but for doing all the initial product development activities, and prototyping is the application where it is used. Then the direct part replacement, you may have some difficulties and challenges of producing an existing part because the supplier may not be there, especially the casting industry is facing some challenges. The casting house, if it gets closed, Then you have to identify another casting house, and then also the tools involved, the die casting tools and other things you have to develop, and then again you have to go through the validation process. In such cases, it is much easier to adopt direct part replacement. In fact, in Honeywell, one of the part which is almost like 40-year-old, in fact, because that aircraft is still flying, they would Honeywell need to support these spares, and then when that spares are required, the casting house had closed their operation. So we come out with the additive manufacturing process, and then in fact this part was certified and approved by the FAA authorities, and then we could what would have taken us more than 2 years, we could have that part certified in less than 4 months. And of course we didn't do any changes to the existing design. Then the part consolidation we talked about, you can, when you're replacing certain parts, you can also look at the adjacencies, and then you can simplify the assembly process which is involved. On the top is the design for additive manufacturing. So that's the big thing, especially when you're designing the new product, and the advantages what I mentioned earlier, all that could be kept in mind while designing for additive manufacturing. One is from the product point of view, other one is from the AM process point of view. You can incorporate all those things into your design and then have. So that is the applications where across industries, whether it is aerospace, automobile, or the medical industries, what I just talked about, or the jewelry industries, everywhere it is being used. Additive manufacturing can also be used for part repair activities, especially on the worn out part. You may rebuild this, and then you can refurbish, and then we can use it. Or during the assembly stages, you have to do some rework to the component, then that can be repaired. And then if you have to do some design modifications to address some of the in-service problems, all those things you can still salvage that part and then can be used. So those are the big benefits why industries are getting into this technology. Wanted to just give a overview of how this thing applications of additive has developed. As I mentioned, in around the 80s and 90s, it was big application was mainly on the prototyping type of activities, and then it was limited to the plastic. And then around in the 2000 to 2010, where the plastic parts were even used for many of the aerospace as well as the medical applications. So that's where the application started getting used for the production applications. And then once the metal additive manufacturing started around 2010 onwards, it is being used for many of the aerospace applications, or many of the space applications, or even the automobile applications. It's being very widely used. And today it is being used for many of the precision parts. The biomedical implants also can be done through additive manufacturing. So that's how the industry has grown. This chart shows the various industries which are adopting additive manufacturing technology. I talked about aerospace, dental, jewelry, the implants, the surgical equipments, then the textile industries, and then the sports industry. In fact, many of the shoes, especially from the standard builders, they do the printing of shoes with additive manufacturing. And electronic PCBs also can be printed today with additive manufacturing. So there's a wide range of additive manufacturing applications today across the industry. Keeping this in mind, recently I was involved in this survey which was sponsored by Ministry of Heavy Industries as well as the Ministry of IT, to see what is happening in the country in the additive manufacturing. And this survey also came out with all these industries: automotive, aerospace, healthcare, construction, the electronics, art and jewelry. So all these industries have in India also it's being used. For example, on the automotive, Tata Motors and Maruti are leveraging additive manufacturing for many of their new product designs for the prototyping, and especially some of the plastic parts, they are even using it for the production applications. In fact, the BMW and the Ford have a very big additive manufacturing technology centers in their global facilities. So similarly, aerospace, all the aerospace industries have been leveraging additive manufacturing. And if any aerospace industry is not leveraging additive manufacturing, then they will lose the competitive edge in getting to the high performing aircrafts. And then on the cost wise also they will lose out, so they will not be able to survive. So that's where the technology is for aerospace and defense applications. So even for the electronics components, Intel, Samsung, Bosch, they have leveraged additive manufacturing both for prototyping as well as for the limited production applications. So that's the across the industry where it is being used today. And then the this additive manufacturing is growing at a annual growth rate of about 28%. The installed talent, the supply is around 20,000, 15, 20,000, and then it's going to grow to around 55,000. The unfilled gaps, which is there today, is about 9,000. Again, this is against the market demand, and then it is going to grow to about 25,000 in 2025. This is keeping in mind the talent is the skilled talent is being developed by the industry as well as the educational institutions, keeping that in mind, but still will have a gap. So this is a big opportunity for the for even the skilled manpower to be deployed across the industries. And what type of skills we are talking about? We are talking about the big one is all the CAD modelers, 3D modeling designers, leveraging the additive manufacturing. So that's the big thing. It is easy to develop this skill because most of them had the CAD development skills. So they need to understand the AM process, the AM designs, and then how the design can be made AM friendly, and then we can quickly build these skills. There is a big requirement even for the softwares. As I mentioned, there is one is the CAD software itself, how the automation could be done around that. Then the other one is the pre-processing softwares. And then there is a lot of simulation tools which are being developed today to simulate the entire printing process. So there's a big requirement for the software people. And then of course the technology consultants. So those are the type of skills what the industry needs. Venkatraman talked about the 2V 3D services. I'll not go in much detail. Basically, we have three components. One is the training, the different types of trainings we are giving. One is the introductory training as well as the advanced trainings. And then we can also provide hands-on training to the industries for a week and for 6 weeks, so that we typically take a complete case study and then they go through the design for additive manufacturing process, and then also gets an opportunity to work hands-on with the printers, so that they are fully capable of deploying that technology in the industry. And if the industry wants any of the additive manufacturing on the strategy for deploying it or on the business development, that's the other area where we support. In fact, we are involved with some 3 or 4 industries today to enable that to happen. Consultancy, design consultancies, if you don't want to spend too much of time, but you want to really come out with innovative products, or you can want to speed up the existing product development cycle time. And then of course, if you want to have a small additive manufacturing lab in your facilities, in all those areas, we can provide the design consultancy. As I mentioned, I have been one of the pioneers, being there in the Indian industry for last 12 to 14 years, typically in additive manufacturing only. And I know who are all the people who play for the big players in additive manufacturing. And then we can leverage some of those facilities which are available to provide these type of consultancies. Then of course, as the printing as a service, whether it is metal or the non-metals and different types of polymers, we have a facility where we have printers in our facility for the plastic printers. For metal printers, we are tied out with people like Wipro 3D or the Intech Solutions or the Objectify. Those are the people with whom we have tied out, and we can provide the printing as a solution. So We have also tied out with the IMTMA in organizing a hands-on workshop on additive manufacturing and 3D printing. It's a 3-day hands-on workshop which will happen in the BIEC Training Center, which is coming up on November 16th to 18th of 18th. It's a 3-day full program which will give a full exposure to the additive manufacturing process, which is applicable for both metals as well as the non-metals. And we have 1-day full program where we give an hands-on exposure to the part design as well as printing with both metals and then the non-metals. So we have optimized on the content so that how the industry can get this best benefit in this 3-day program. Registrations are open, and then the participants who are interested can go ahead and register. This is a minimum number of participants what we are targeting. It's only the maximum of 20 people whom we are targeting for this, because it's an hands-on, and you want to ensure that there is a lot of personal touch, and then everybody gets that opportunity to learn. These are the topics which you are covering as part of this 3-day workshop. We'll give a complete technology landscape, talk about the details of the process which I just mentioned today, but each of the process is a technology. So we'll talk about all those details about each of those processes, and then the different 3D printers which are available for each of these processes, and then the details about all the materials. As I mentioned, materials is a big technology around the material science as well as the metallurgical aspects of it, and then how the quality of part is affected by that. We'll talk about a lot of applications, and then the pre-processing models, how as well as the design for additive manufacturing approach, and then what type of post-processing is involved around these things. We'll have a mini project of which will design the models and then go ahead with the printing, and then we'll also have the hands-on with the. So this is what is being planned on November 16th to 18th at BIEC Training Center. So I thought I'll just mention about this in this webinar also.